So as I mentioned, I mean, this shows you that the original system with 56 key size can be actually broken, and nowadays with computations can be broken in less than an hour, much less than an hour. Accordingly, other systems came into the story. So you have the advanced encryption system, which is still symmetric, but it's different from the DES. I'll mention in a minute what's the difference, the main difference between them. We will not go into the AES. It requires another background in mathematics. I will give you simply just a couple of hints on that background in mathematics, and then how the AES is slightly different from the DES. But the idea here is for the AES, the advanced encryption system, use key sizes of 128, 192, and 256. So really larger, and you can see the difference in terms of computations. Even if you reduce this, because we have higher computations right now, you probably reduce it by dividing over 100, which is still gonna be 10 to the power 15. So that's a much larger number, and this is in years. So it's not a small number at all, okay? This is really a very long time to break the system. Also, the DES itself was maintained, but the key was increased to 168, which gives a 10 to the power 29, maybe you could say 27, for example, in nowadays computations, in terms of number of years to break the system. So that's really a very long time. Triple DES is simply larger key, that's number one. And number two, it's DES performed 3 times, each time with a different key. Oh. So you have 3 keys, each one is 168, and you take your data, you use DES with 168 encryption. After that, you take it through another key, 168 bits, and you take it through DES full number of rounds, and then a third key, and then you perform the full encryption at that point, right? So that makes it really very complicated, and brute force would not work, and even other analysis techniques will take a very long time to break the system, okay? On the other side, the AES system, so let me just quickly give like a hint about the AES. So for AES system, remember when we studied the number theory, right? So for a primer on AES, okay? So when we studied the number theory, number one, mathematical background. We studied earlier, if you remember, the number theory, right? And as part of that, we looked at mod arithmetics, right? So performing any operation, mod something, okay? Now, the idea when we were looking at DES was relying on the fact that we use some finite alphabet, and because of that we have some mod arithmetic included in our operations. And then we have some keys that are hidden, nobody knows about them. And for that person to figure out the keys, they have to either do like some kind of brute force trial on the keys, or map the information back to the statistics of the plain text, if they can, which is called cryptanalysis, right? All what we needed as a tool was to understand how modular arithmetic is performed, okay? And the operations that we discussed were discussed from kind of a logical point of view. You take this, you apply a function to it, which is a mod function, right? And then you end up with, we didn't really have equations. We were not solving some equations in a modular way, okay? The idea of the AES is that it relies, in most of its algorithms, it relies on arithmetics that uses equations rather than arithmetics that uses logical operations, such as permutations or even the substitution operation, okay? And those arithmetics relies on a conceptual field in mathematics, generally falls under abstract algebra, and in particular inside abstract algebra, the primary field is set theory. Inside set theory, you have classification of groups of elements and operations, right? When you have this classification, we fall under the initial one is called a group. You remember what's a group? So you have a set, right? Which is just a group of elements, like a collection of elements, A, B, C, and so on. It can be finite or infinite, and the elements are not repeated inside, right? Okay, that's a set. And then we have something called a group. So what's a group?
It's part of the set.
No.
Sets.
Plus, set plus what?
What's not in the set?
No. So a group is a set, A, B, C, and then an operation, whatever the operation is. Typically, it's an addition or something similar to addition, right? And for that to be defined as a group, we have a condition that when you perform this operation, the outcome is one of the elements of the set. So when you add two elements from the set, for example, if it was an addition, the result is going to be something that belongs to this set. It cannot be something outside the set. If this happens, we call this a group. Okay. Now, in addition to a group, there is something called field, which has two things. It has a set, a couple of operation. One is similar to addition, so we say plus operation, and one is similar to multiplication. Okay, so it has two operations, not only one. Again, when you perform those operations on the elements, the output should be belonging again to the group, right? And we add to that a few things. It's actually existing since the group, that for the operation, there is a unitary element, which is when you perform the operation using that element, the output is the same element. So A operated on with unitary is going to give you A again, okay? And you have an inverse. So there is an inverse for A that belongs to the group, which is when dotted with A will give you the unitary operator, the unitary element, sorry, okay? So for a group. Same thing for the field. You have for each one of those operations, the one that resembles addition and the other one that resembles multiplication, you have a unitary element and you have an inverse. Okay? طيب. Now, if we are dealing with mod operations, so if we are dealing with modular arithmetic, remember that for addition in modular arithmetic, we always had an inverse, right? We studied that earlier when we studied the modular arithmetic. But in some cases we had a multiplicative inverse, in some cases we didn't, right? You remember that for modular arithmetic, or I forgot it?
There's a table with two columns.
Yeah, I gave an example of a table, mod, it was mod what, 19 or something like that, right? And then we looked at the different operations. We found that for all addition operations, we can actually, for all elements, there is an inverse. That when added mod whatever, will give you 0. 0 mod the same, right? But multiplicative, which is when multiplied by that, will give you 1. It happened to some elements, it did not happen to other elements. And then the idea was, if the elements are mutually, what do you call them?
Exclusive.
No, not exclusive.
Mutual factors.
No. If a number and a number, they don't have any common factor, we call that prime.
Mutual prime.
Yeah.
Mutual
So,
prime.
yeah. So if these elements are mutually prime, we call them this. No, it was something prime, but not mutually. Relatively prime. Yeah. So if the two values are relatively prime, right, then in that case we will have a multiplicative for all elements in the set. Okay. The only way to do this, and we are talking about the element and the mod, the index of the mod. Okay. For all cases, if the mod is prime, so if we are doing mod to a prime number, this means that all the elements here will not have any common factor with the modular index, right? Because all the elements there are gonna be what? 0, 1, up to p minus 1, right? And none of those will have anything common with a prime number, right? Okay? Because that's the definition of a prime number. It does not have any factors except one, okay? And itself. So this means that all the elements inside our field, right? All the elements inside our set will have also a multiplicative index, a multiplicative element, right? A multiplicative inverse, okay? So the condition for a field to work in integer numbers, the conditions to have a field in integer numbers, which includes addition and multiplication, is that you perform your operations mod some primary number, right? Those kind of fields, we call them Galois fields, GF of P. Okay, so again, what's a Galois field of a prime number P? It's the set of elements, integer elements, right? Starting from 0, ending with P minus 1, where P is a prime, okay? And includes addition and multiplication operation. That's the Galois field of P. This is the set that includes the numbers from 0 to P minus 1, where P is a prime number, and includes the addition operation and the multiplication operation. خلاص كده؟ تمام؟ So that's modular arithmetic that we studied, but only mod a prime number, P. خلاص? Again, why did we need this? Because now when you look at AES, AES is very similar to DES with only one difference. That the operations performed inside, again, it includes rounds, it includes both permutation and substitution, but all these operations are represented as equations, okay, on a GF of some prime number P, on a Galois field of some prime number P. Since we didn't really go into the details of more advanced modular arithmetic, we are not gonna study those operations and the equations and how to map these equations to polynomial equations and all these aspects. But anyways, the main concept, you understand it, that it's again a set of substitution and permutation operations with a larger key size. The minimum key size is 128 bits, right? And those operations are described in equations that falls into the Galois field representation. Okay? That's good. That's all what we need to know about AES. We're not gonna study more about AES in this course, but you have the chapter. If you want to review it, go ahead, okay? It's still a symmetric key, so there is a single shared key between transmitter and receiver, and it has to be exactly the same key. They both perform the equation and the inverse equation, so some equations are performed in the encryption, the inverse of these equations are performed on the description and the decryption side, but everything is described in polynomials or equations, rather than in the case of DES, because that allows more freedom and more unified implementation, right? In the DES case, we were describing things logically. You perform permutation, and here is the table that shows you how to do the permutation. You perform some function, and here is the table that tells you for each input what's gonna be the output of that function. Here, it's different. It's actual equations, okay? So there is no conspiracy theory more here.
For DES, I feel like because you have a logic and you have to turn it into math to find the inverse, but in AES you already have the math, you have the algebra, it would be more straightforward to find the inverse.
Yes.
Is that true?
It's two things. A more structured way to kind of implement the method. So for implementation, it's easier, it's faster, because in any programming, if you represent thing as a mathematical equation, typically the execution is much faster, and the programming is easier, so representation. The other thing is, because of that structured mathematical representation as equation, you can develop the system and you can analyze the system much easier. So if you want to understand its behavior, it's just a derivation of a set of equations, right? If you want to develop enhancements, you can figure out easily, based on the structures representation in equations, how to enhance this part or enhance that part by modifying this equation, by removing this characteristic of the equation or adding that characteristic to the equation, and so on. So it's a more mathematical oriented approach rather than structure and logic oriented approach. Okay, that's the main difference between the two methods. In addition, of course, to that the operations are more mature and the keys are larger and so on. Okay. Okay. Going back to DES, I discussed last time, and I will mention it again here. DES by default, because of the Fiestal implementation inside it, it hides actually anything related to crypt analysis. So you cannot really perform crypt analysis on the system. Yet, there is an attack called timing attack. Timing attack is reliant, again, what's the objective of any attack? To figure out the key. If you figure out the key, you are done, right?
Yes.
Typically, when you attack the DES system and more advanced systems than the basic block ciphers, you are not using crypt analysis, but you are using some information related to input-output. So you have some cipher text and plain text that are known, a set of cipher and plain text that are known, right? And then you rely on getting more of the cipher text eventually to kind of do that interpolation that I talked about. One other side that you can use to attack is that there is a slight difference in any computational operation between computing operations that includes all zeros and operations that includes ones and zeros or ones and ones. Okay? The one with ones are typically a little bit slow. Has to do with the transistor implementation and stuff like that. Okay? So if you can do some analysis having some known plain text, cipher text.
On the time it takes to
Exactly. So you do timing calculations. You know that what came right now is a full cipher text. How long it took it to calculate, right? And if you have some information, what was supposed to be the plain text, you can you can figure out eventually with some longer analysis the number of ones in the key. You cannot know exactly where they occur, but you can figure out that this key approximately includes, for example, half of the bits are ones. By doing this, you reduce the search space significantly, right?
Yes.
Because now you are searching only among the different combinations of ones and zeros that maintains a certain number of ones.
But it's approximate, right?
It's all of this is approximate. So you might say maybe a little bit more. So maybe it includes maybe, for example, 6 ones, maybe 4 or 8. So it's somewhere between 4 and still you have reduced your search space significantly,
How
right?
often does this happen?
Yeah.
This type of attack?
How often means what?
Like,
How long does it take, or how
like,
often?
are they still using it?
It is a current, but it's in most of the time it's not sufficient. It's a weakness, but it's not sufficient to really within a reasonable time to break the key. Because of two things again, because of the fact that there is an error in what you calculate, and the reduction, because of that error, the reduction in the search space is not sufficient to make the computational time much less. But it's a weakness. At some point, it might become a point to break keys, right? But not now. I don't think now it's sufficient to break keys, okay? So that's just a mention of a side weakness of the DES. But so far, we haven't heard, at least myself and the text over there or the literature, did not mention any cases where an actual DES system was broken using the timing attack, okay? There are few principles in the design of DES, right? And the greater the number of rounds, and we mentioned that, the more difficult is to perform crypt analysis. So you protect more against crypt analysis by doing more rounds of encryption. And the criterion should be that the number of rounds is chosen so that known crypt analytic efforts require greater effort than a simple brute force. I mentioned that earlier,
Yes.
right? And for the case of DES, if you stop at 15 rounds, okay, then in this case, a crypt analysis would require less effort than brute force. Once you go to 16 rounds, okay, the mathematical is not provided here. That's way beyond even my own capability because I'm not specialized in this domain. It requires me to study for it to figure out how they do the mathematical proof of this, right? But it was found, given a particular mathematical analysis of the system, that if you stop at 15, a brute force attack would be more complicated rather than breaking the system using its own structure and cryptanalysis. While if you go to 16, then brute force becomes a simpler way. So basically now you reached the ultimate in any case is to reach brute force, because brute force means I have no clue, I'm just trying everything, right? And then the strength becomes how big is your key, and for larger than a particular number of bits for current computation, it's impossible to break the system, right? When you are designing the function f, remember I mentioned earlier that one characteristic is that it should not be linear enough. It should be as far as possible from being linear. It should be complicated enough and away from being linearizable, okay? The other important feature is to achieve two important things. Something called avalanche criteria and something called the bet independence criteria, okay? The avalanche criteria mentions that, okay, it's intuitive, but there is no mathematical proof to it in what we study in our case.
Conspiracy? Is this also conspiracy?
No. The avalanche, no, these are desired mathematical properties, okay? That any output bet of an S box should change with probability half. I mean, this explanation is more or less related to how the S box operates. But let me give you a more qualitative description. What's the avalanche? The avalanche says simply that if your input changes by a single bit, so if you have two inputs, the difference between them is just one bit change, okay? Or for the same input and two different keys that differ from each other by a single bit, the output that you get from the system should be quite different. Shouldn't be only one bit difference or two bits difference, because otherwise figuring out the key is going to be much easier. Breaking the system is going to be much easier, because you will have lots of occurrences where two inputs are with only one bit difference, or two keys that you use are only with one bit difference, right? And then accordingly, you can figure out by some kind of either inducing inputs or having access to those particular inputs and their corresponding outputs to figure out the key, right? If a single input change is going to cause only one single output change, or a couple of bits only to change in the output, right?
So it says any change in the input or the key
Yeah.
will lead to a total different.
Any single bit change will lead to a lot of bit changes in the output,
Okay.
not a single bit change, okay? This is why they call it the avalanche. Okay, so single change at the input will cause big difference in the output, like when avalanches happen over snow over mountains. You were saying what, Time?
They're more similar to the SHA-256.
The what, sorry?
SHA-256 amplified. Even if you change a single bit, the output changes a lot.
I didn't hear the
SHA-256, SHA-256.
SH.
Encryption.
The encryption method, yes. That's the same property. It's not very similar, it's the property. It's the same property in that encryption method, yes, okay? And the other one is the bit independence criteria. And this again, the bit independence criteria says that, again, if a single bit at the input changes, what does it say here? State that the output bit should change independently when any single, yeah. So not only that the number of bits is going to be much larger, but also the pattern of change should be independent from which exact bit has changed in the input, the location of the input bit change, okay? So that again gives you kind of the confusion operation. So you cannot really relate which bit had changed when you see the pattern of the output, okay? These are two important properties and mainly are achieved by the function f, the way the function f is defined, the encryption function, and the derivation of the subkeys. Because again, if you derive the subkeys in somehow a wrong way, this is called the key scheduling algorithm, okay? So if you derive them in a way that does not allow them to be different from each other sufficiently and different from the original key, you will not be able to achieve the avalanche situation, okay? Because remember that the subkeys are used in the different rounds, and the result is going to be the combination of all rounds that you use over there, okay? And this slide is just mentioning that the subkeys are first of all, they should allow difficulty for deducing to work backward to the main key from the sub keys, and also they have to achieve a certain property to be supportive for the avalanche criteria and bit independence criteria. Okay, that's it. We are done with what we need to understand and we know about the DES. I said we'll finish earlier, but yeah, 15 minutes is good enough.